Okay, so
Oh, yeah.
10.5 talks about finding probabilities of independent and dependent, okay? 10.5 is independent, and once again, it's formulas, and dependent probability. Okay, now, if probability of an independent event, independent. Okay, independent event looks like this. The formula for independent says, probability of A and B equals the probability of A times the probability of B. So yesterday, we did A or B, correct?
Yeah.
Okay, for both of them, it was A or B, and it was adding. If it says and, it's multiplying, okay? So, two events are independent if the occurrence of one has no effect on the other, okay? For instance, if a coin is tossed twice, the outcome of the first toss has no effect on the outcome of the second toss, correct? Okay, it's just 50-50 either time, okay? So, here's the first example that goes with independent. For a fundraiser, a class sells 150 raffle tickets for a mall gift certificate and 200 raffle tickets for a booklet of movie passes. So 150 tickets for the gift card and 200 tickets for the movie passes, okay? Interesting. Okay, then it says, you buy 5 raffle tickets for each prize. Okay, so you bought a total of 10 tickets, 5 each. It wants to know, what's the probability that you will win both prizes? So how do I set that up?
5 over 150 is out over 200.
Good, 5 over 150, right?
Yeah.
Times 5 over 200. So 5 times 5 is 25. What's 150 times 200?
Well, this is a question. Could you just
Reduce first?
Yeah.
Yes. So if I reduce first, this changes to 1 over 30, 1 over 30?
Mm-hmm. Yeah.
Yeah. And then this one changes to 1 over 40?
Yeah.
So then you get 1 over 1200?
Yeah.
And that's your probability.
So it's much easier just to reduce first.
Yeah, it would be,
If
if you can notice that, yes.
If it's, will it always be easier to reduce first, or?
I think it is personally, but it's kind of up to you. If you see it, yes. If not, always reduce at the end.
yeah, that's it, because you're gonna have to reduce.
Yeah.
it.
So either way is fine. Okay. So that is when you have an independent event. Does that make sense?
Mhm.
Independent, okay? We got several more examples. In a BMX meet, each heat consists of 8 competitors who are randomly assigned lanes from 1 to 8. Okay, 8 competitors, lanes 1 to 8. So, you have lanes 1, 2, correct?
Mm-hmm.
Okay, there's your lanes, you're assigned 8 competitors. And it wants to know, what's the probability that a racer will draw lane 8 in the 3 heats in which the racer participates? Okay? What's the probability of him drawing lane 8 in race 1?
1 out of 8.
What's the probability of him drawing lane 8 in race 2?
1 out of 8.
What about race 3?
1 out of 8.
Boom. And 8 cubed is 512, is that right?
Yeah.
So you can leave it like that, or you can give me a decimal, because it said probability. So, 0.002.
Fraction is okay.
So he has 0.2% of a chance of getting lane 8 all 3 times. Okay? Independent. Okay? While you are riding to school, this is old. This picture's old. It says, while you are riding to school, your portable CD player
Bruh.
randomly plays 4 different songs,
We
okay?
call it, it's called iPhone, not scored.
Okay, so it randomly plays your music device. How's that? We'll change it to music device. Your music device randomly plays 4 songs, okay, from a CD with 16 songs on it. So 4 of 16, it plays 4 of 16.
Thanks a lot.
What's the probability that you will hear your favorite song on the CD at least once during the week? And the week has 5 days in it. Okay,
Wait, so we have 4 in
Well, there's
today,
4 out of
or-
16,
so there's 4 out of 16 songs,
but there's.
and you want your favorite song once out of the 5 days of the week. Yes? 4 out of 16, favorite song once out of the days. Now, in my opinion, it would be easier to do 1 minus what we don't want
Mm-hmm.
than to try to figure out that math, because that would be crazy. So we know that we want 16C4, right?
Yeah.
Okay, 16 combination 4. But that is what we want to divide by, because we know that we're having 4 songs each day. There are 16 options,
Oh, actually, we're doing it.
okay? Now, not hearing your song would be
15.
15C4, okay? Because I would have 15 songs that I don't want to hear. Does that make sense?
Ouch.
Now,
That's
how many days is that?
5.
So this is to the 5th power,
Oh, no.
and it's 1 minus that. Yes? Does that make sense? Instead of doing 16C1, 16C2, 16C3, you know what I'm saying? We can do it this way. Now we have to figure that out. What's 15C4 divided by 16C4? Start there, because it would make it easier.
0.75.
Okay, and then raise that to the 5th power,
0.23.
and then do 1 minus 0.237. Let's do that.
And then that should be, oh, wrong way. 0.76.
0.763. So you have a 76.3% chance of hearing your song. It's pretty good odds, yes? Okay.
I mean, with 16 songs, good. Decent.
I know, right? Okay, now, let's talk about dependent events. Dependent. Dependent has a formula that looks like this. Probability of A and B, okay, this one's a little bit more complicated. Probability of A and B equals the probability of A times the probability of B divided by A.
Okay.
Okay,
Is there anything where it's P probability of B times probability?
No.
Okay.
okay. So, the table, so dependent events, 2 events, A and B are dependent if the occurrence of one affects the occurrence of the other, okay? The probability that B will occur, given that A has occurred, is called conditional probability and is written as P B of A. So it's written like this. Technically, it just goes straight up like this. But this is called conditional probability because B is reliant upon A happening first. So A has to happen and then B can take place, okay? So when you enter like a contest, okay, and they say you have to make it into the top 10 to then be considered for to win,
Oh, yeah.
does that make sense? You have to actually hit the top 10 before you can actually get to the finals, okay? So it's kind of like that. Tournaments are a lot like that, yes. When you're doing March Madness, it's a lot of this type of probability, right? Your team has to win that you chose and move on in the brackets in order for you to get points, right? And get to the end. So that's where this probability comes in, which means it's a higher chance of you not having what you want, correct? Because things are reliant upon the other. whereas the independent is just straightforward probability, this times this, okay? So then they give us this, table, let's talk about, actually, let's skip and do this one. You randomly select 2 cards from a standard deck of 52 cards.
They love cards.
What's the, yeah, because it's an easy thing to deal probability with, that's all. Dice and cards are easy. What is the probability that the first card is not a heart and the second card is a heart? So, not a heart. And then you want a heart. Okay, what's the probability that it's not a heart and then the probability that it is a heart? Okay, is that dependent or independent? Think about that first. Does drawing a heart the second time depend on if you drew a heart the first time?
Well, it's
No.
dependent. So,
What? Well.
Well, yeah.
Cole says no.
I mean-
Yeah, because you're reducing the amount of parts.
Mm-mm,
No.
this
'cause-
is not a heart.
Oh, I
This
thought you-
is-
You
okay,
need to
no,
know
no.
how many hearts there is so you can, figure out whatever.
Okay, listen, this example, this first part is independent.
Oh,
Because not a heart and then a heart doesn't matter what I draw, because they didn't say that I can't put it back in. Does that make sense?
oh.
So every
Oh, that's-
time I can draw from 52 cards. Does that make
So should we
sense?
just always assume that we can, do that?
It'll give you words, yes, if not.
Right.
So what's the probability of drawing not a heart? How many, there are 4 suits and each suit has how many in them?
13?
13, so 3 suits of 13 is
39.
39 out of,
52.
and then you're gonna multiply that by,
13.
can we reduce any of these before we go on? Yes.
Yes.
This can be reduced to what, 3/4?
Mm-hmm.
And this can be reduced to 1/4?
Mm-hmm.
So you have 3/4 times 1/4, which means you get, that's the probability of drawing not a heart and then a heart. Okay,
Oh.
part B says this. Okay, now you do not replace the first card.
So now, okay.
So now you want to draw not a heart and then a heart without replacing the first card. So is it reliant upon the first draw now?
Yeah.
Yes. Okay, see the difference there?
So,
It's a little tricky.
so if it says do not replace, then it's always gonna be different.
Correct.
So that's-
Okay, so what's the probability of drawing not a heart still? 39 out of 52. Now, I need to multiply it by this, correct?
Yeah,
The probability of B over A. So the question is this. How many hearts do you have to choose from? 13. How many cards do you have to choose from?
51.
So it's 13 over
51.
51, okay? Which means this reduces to, once again, 3/4, correct? But does 13 over 51 reduce?
No.
No. So you have that times 13 over 51, which would give you 39 over 204, correct? Does that reduce at all?
Yes.
Good question.
What?
Oh, that, they did it differently.
It does not.
Yes, it does. They
That's
reduce
what
it, both are divisible by 3.
I thought.
Which gives you 13 over 68. So that's your probability
Interesting.
of a dependent event. Okay? Let's look at one more.
I'm confused with the formula for that.
It's right there.
Probability of B over what's left, basically.
Oh, okay.
Does that make sense?
And also because we used the one card, it makes it 51.
Right. So because we didn't replace a card, we only have 51 cards
Yeah.
now to draw from.
Okay.
Okay. Costume party.
Oh, boy.
I know. Drew loves costume parties. You and your 2 friends go to the same store at different times, okay? To buy costumes for a costume party. There are 15 different costumes at the store. So you have 15 costumes.
Everyone in the party can see the exact.
That could happen though.
Okay, 15 costumes.
That'd be awesome.
What's the probability that you choose different costumes? You and two friends.
Well, there's 15 costumes.
You, friend one, friend two. Okay, and you want all different costumes, correct? So so if you go first, how many costumes do you have to choose from?
15.
So you're gonna choose you're gonna choose 15 over 15, right? You have 15 out of 15. Okay, if your friend goes next and you don't want to repeat, what do they have to choose from? 14 over 15. And if your second friend goes, what do they have to choose from?
13.
Okay, this is dependent,
Yeah.
okay? It's the probability of A and B, okay? Equals the probability of A, that's this first part right here, yes? Times the probability of A, or B over A, yes? Or B, A, because it's dependent on that. And then times the probability of C, A and B.
Where do you see from?
Because there's three, so we have to
Oh,
keep
Jason.
going. It can be more than two people. You have three people.
Mhm.
So look, this probability is just straight up the probability, yes?
Oh.
This probability is dependent upon this one, correct? This last person's probability is dependent on what came before and what came before that.
So the third person's his friend too?
Yeah.
Oh.
Does that make sense?
Good.
Okay?
Yeah.
So then you would multiply all of those out and you would figure out what you get. So 15 over 15 is 1. And then you have times 14 over 15 and times 13 over 15. Right. So 15 times 15 equals 225. 14 times 13 equals, well, if I could press the right button, that'd be good, 182. So you get 182 over 225. If I divide that out, you have an 80.9, 0.809. So an 80.9% chance of showing up to the party in a different costume than both of your friends. Okay? This is what you're working on today.
Oh. Okay.
Oh,